Hi everyone, let me illustrate how we use StatKey to look at correlations between two quantitative variables. So we're in StatKey here. Where we're going to go is this two quantitative variable. Again, this always comes with a bunch of data, but we're going to use our own data. And for this example, let me go and use an experiment where what I'm going to do in that experiment is I'm going to measure the spring constant of a mass on a spring and measure the period it takes. The period is the time it takes to go back and forth. Okay, and I measure the spring constant. The spring constant kind of measures the stiffness. And I somewhat made up the number here, so these are nice. 1, 2, 3, 4, 5. These are just kind of different springs, which I know the spring constant. And these are not really realistic numbers. The theory behind this is that the period of a mass of a spring with a mass is 2 pi. This is the mass in the spring, and this is k is the spring constant. Okay, we'll see this very soon, but you don't need to know this for the moment. The point is, let's say I want to do an experiment, and I'm measuring the spring constant k and the period, and I want to know whether these two things are correlated. So I did that. I have a spring constant and period. I save. I guess I'm actually make sure I'm going to save has CSV. Replace. Yeah, feature. How is that? And then I go back to my StatKey. I upload the spring fit right there. I choose this as my x variable and this is my y variable. It's like okay, and here it is. So it tells me the mean period, the standard deviation. I have only 5 data points, and it tells me they're pretty strongly correlated with a correlation of 0.93 and negative. If you show the regression line, this is what it looks like. So already we know that yes, if the spring has a stiffer spring constant, it will have a shorter period, which makes sense. But so that's great, and that makes sense, and they should be correlated. But this is already 0.93 in physics is not that amazing, and even just by looking, I can tell well this is not really a straight line. In fact, it looks like an hyperbole. And so, since I know from theory that the relationship should be not t is equal to something times k, but rather the period is equal to something times 1 over square root of k, I can go back in my Excel file. I'm going to add a column, and I'm going to build that relationship by simply saying I'm going to take, instead of spring constant here, I'm going to do 1 over the square root of the spring constant. So I go here, and it says it's 1 divided by, and in Excel you can enter, there are some codes like square root is XQRT, then you put parentheses, and then it tells you, oh, you're trying to do a square root. You tell them of which number, say this one. You close the parentheses, and now I just did great. 1 over the square root of 1. That's 1. Not very surprising. But I can then drag this formula down. And what it did there is it took 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, which is 1 over 2, 1 over the square root of 5. I save. Yes, I save to CSV. I go back to this. I upload the file again. Spring fit. But this time I will take this as my x variable and this as my y variable. And now I have a complete linear relationship as we expect in theory. The correlation now is 0.999. This is actually really high, and this is a bit because it's a made-up experiment. You can also see the slope. It tells you the thing in front of the coefficient and then the intercept. Right, we're going to do this very often, so you got to get good at this, and you got to be able to realize, oh, I need to switch. Okay, so there is a linear relationship. Again, there is a linear relationship between the period and 1 over the square root of k, and this is what this is showing. Period, and this axis here is not k; it's 1 over the square root of k.